So hello, everybody. This is my second time in Barcelona. So, very nice to be here, and I hope everybody had a good night last night and fully recovered by now. So we want to talk about database apps in WebAssembly. Why? Because one of the goals of dreams of WASI or WebAssembly on the server side is to run WebAssembly as like the JVM on the server side. When people hear about that, the first thing they try is the database application. They try to connect it with database because that's how Java started. That's how Ruby on Rails started. That's how Node.js started. You have a CRUD application that babysits a database. That's essentially, I would argue, most Java applications today still do that. That's all they do. Just have a transaction manager, JDBC, and all that sitting in front of the database. However, let's before the however, one of the things that WebAssembly on the server, one of the value proposition is that it's lightweight, it's fast, it's secure. So hence, it's great for microservices. The way I look at microservices is for internal use, serverless functions for external use. So they are the same thing, just two sides of the coin. So if you look at all the microservice design patterns, they all have database in there. There's even a best practice to say one database per service, right? You need to have one, each microservice needs to have its own database. So, it's database or key value stores or NoSQL databases. There are lots of ways to do that. But in the end, you need some kind of data, that's accessible to your microservice or to your WebAssembly functions in order to be considered a real thing. Because otherwise, coming from the EJB land, there's the session beans and entity beans. And the session beans are beautifully designed. It's stateless, it's scalable. However, it's not that useful. It's everything useful that you want to do almost all have to have some kind of database in it. So there's 4 ways to do to connect database to a WebAssembly application. The first, I think, is the most common way to do it is today. Essentially, all the popular WebAssembly runtimes do that today, including Fermyon Spring, and I think Wasm Cloud and Suborbital, and it's all to have some, to encompass the database into a host functions and expose that host function interface into WASM, right? I think this is what I would consider is it's a high-level approach, which is great. That's I think all those projects have seen great success with that. But one of the potential issues with that is it requires the developers to learn a new thing, a new API. There's I think for a lot of greenfield applications, it'd be a great way to do that. However, in our practice, we also deal with a lot of legacy applications when there's code written already, and people do not necessarily want to rewrite their code to a new API. Can we do something with that, right? And then the second approach, really, I'm going to talk about, I'm going to talk about second approach, is to embed the WASM in a database. That was the talk given yesterday from libSQL, which is MySQL, SQLite on the edge, right? Because we worked with them to make WASM into a host function, into a UDF, a user-defined function, into that database. So we sent out a tweet at the time to say this allows user to store image as a blob in the database, and then just use SQL to query what's on the image. So you can do things like that. libSQL select a WebAssembly-defined function. It's called classify, and the parameter to that function is a field is a column in the database, and from the images is the name of the database where ID equals 1. So ask the SQL statement to perform this function on the field in the database, and the blob is that JPEG image that's up there is Dr. Grace Hopper. So when you do that, it gives the result. The SQL statement tells you this is what's on the image is most likely a military uniform. So you can see the example here. But that's another approach to do it, is to just embed WebAssembly into a database, right? And the database itself may also be embeddable. So that allows you to have embedded stateful functions. But that approach is still not the microservice approach we are talking about. The microservice approach calls for the WebAssembly application or the service run side by side with the database, more like the old ways, the JDBC or the ODBC approach, right? So that leaves. So I'll go back to my previous slides. So that leaves the third and fourth option. The third and fourth option is, the third is just, is there a way that we can just reuse existing database clients and libraries that people already use? And the fourth is that, can we reuse some of the more, I would say, advanced patterns in microservices, like sidecar runtimes? So those are the main topics that we're going to explore in this talk for the remaining 24 minutes in this talk. Okay. So what do we mean to just use a database client you already knew? So this is a sample application that we wrote that runs on Wasm Edge. The great thing about this conference is that I don't feel like I need to explain Rust code, right? Because most of you guys here already knew Rust. And you can see at the top left, there's a main function. It's written against the Rust Tokyo API. What it does is that it's open a database connection pool. It's a pool of 5 connections and put that into a pool. And then extract 1 connection from the pool. And then the other 2 panels, one of them is just to insert 5 orders into the database, right? So the orders is it's a little bit, I would say a poor man's ORM. That's it doesn't really do relational mapping, but it maps the Rust structs into the database table, right? So you can see that it's turned into a SQL statement, and then use using the Rust statement to send those 5 send those 5 inserts as a batch into the connection, and the other side is to select from the orders, and when you select from the order, you iterate through the 5 orders and print them out, right? So the library we are using here is called MySQL Async. It's an asynchronous MySQL client. Why it's important? Because WebAssembly is fundamentally a single-threaded environment. So we ideally we should not have the database connection blocking the main execution thread, because one of the use cases would be you have a HTTP connection coming in and have a database connection on the other end. You want those to be non-blocking. So while you are waiting for the other data to come in, you can query the database here, right? So so that's to have it non-blocking drastically improves the performance. So it's a fairly popular a database client in Rust. So if you want to see the whole example, you can go to the GitHub repository down there. Which but now we're going to get into a little depth about what we have done. So let's give an example. Let's give a complete example to see how how the MySQL Async and MySQL Async works in a WebAssembly environment. So this is a overall architecture diagram, and you can see this is just I can show this diagram like 25 years ago for the Java crowd. It'll be the same. It's a 3-tier architecture. There's a web server in the front, there's an application server in the middle, and there's database at the end, right? And except with WebAssembly, because you can scale to 0, so you don't have a heavyweight application server sits in the middle. Instead, you have a lot of service functions that sit in the middle. You can have these consume very little resources. So in the jargon of the containers, that's we would have those the sidecar or the HTTP server in the yellow boxes, and then the WebAssembly container in the green boxes. So this is a very I would say a very typical microservices architecture that's should be really familiar for most people coming from the server background. So let me exit out of here and show you the live demo. So the demo is just pull this GitHub repository, and you can see there's a bunch of files in here, and it's set up with Docker Compose. So let me try to show you the Docker Compose file here. It is very simple. You just have 3 containers, like I just draw on the previous slides. So there's at the bottom there's a database which is a MariaDB, and it set up a root password. And at the top is a client, which is an Nginx container. And the Nginx container responsible for outward HTTP connection. So when the HTTP connection can come in, it serves the static content. And then the server in the middle is written in Rust and compiled to WebAssembly. And what it does is that it listens to HTTP port, listens to incoming connection, and once it receives incoming connection, it transforms that into database queries against the MariaDB on the back end, right? So it's a very, I would say, it's a very normal setup. So now let's look at the code for the WebAssembly application. So let me go right. The whole thing is 200 lines of code, including comments. And perhaps, that's the main function is perhaps the most important. As you can see, it not only opens a database connection, as I've shown in my previous slides, but also opens a HTTP port at 8080. So it itself acts as a web server. So that's the use case I just talked about. You have a non-blocking web server on the one end and non-blocking database connection on the other end. So you can, those two can work at the same time. They don't have to block each other. So, so this is really the essence part of the whole thing. So you open a web server and you open a database connection, and then there's the rest of the program are all functions in terms of how to handle the incoming HTTP request. So for instance, here you can see if the incoming HTTP request is get orders, I would get a database connection from the connection pool and run this SQL statement to select from orders, right? And then iterate over the result to show you the orders, right? So that's all very normal. Just the 4 operations: create, read, create, read, update, and delete, right? So for all operations are here. The whole thing is 256 lines of code, including comments. So this essentially is the whole application. Now, the way I run it is I use Docker Compose. I can't see it. Docker Compose up. So what it does is that it takes that Docker Compose file, the 3 containers, to build the entire application. I don't even have Rust installed on this Mac, but because Docker set up the environment for you, so it knows how to put all the dependencies in a build container to build it, and then create a deployment container, and then to do it, right? So what it does is that because I built it before, so you don't see the very lengthy process of Rust compiling, but now it has all started up. So it start up a Nginx server, start up a MariaDB, and start up the WebAssembly-based microservices in the middle. And now we can go to Docker Desktop and see it in action, right? So see, here's the containers. And because the Docker Compose put all those into a group. So you can see there's 3 things here. There's a client, which is Nginx, and there's a server, which is, it's labeled as WASM, so it's WebAssembly compiled. And then there's a database. And because the port mapping is done in Docker, so you can just open a local web page. It's localhost, and it's Nginx serves you the static web page, and then you can say I want to add an order to the database, just give some random ID, quantity 2, amount 20, tax 2, it's shipping. Okay, 3, and say it's 123 Main Street, whatever, and then I say add order. It sends the order to the microservice. The microservice sends the order to the database. Now it's added, and you can see it at the top. You can keep adding orders. You can delete them. It's all from the web, from this web interface, right? So that's one interesting thing about this demo I want to show you is the size of the images. You can see this one. This one is the WASM image. It's what we call the application server. The total size, I did not do any optimization, and I put an AOT binary in it as well, so it's 3 megabytes. Okay, so the whole thing, a very typical application server is now reduced to 3 megabytes in a container. If you look at everything else, like the MariaDB, it's 110 megabytes. Nginx is 16 megabytes. Just imagine if you do the microservice in Java, you would need the Ubuntu-based image, you need the JVM, and you need a bunch of stuff, and you could easily be 100 megabytes, right? If you do that in Python, just think about, that's, they could all very big. Someone argues, say, but that's not a fair comparison. Why can't I just compare Rust to native and that put it into an empty container? Wouldn't that be smaller than that? In fact, first of all, it's not smaller than that. The second, that essentially breaks all the portability of the thing because that's compiled Rust binary would be very dependent on the underlying CPU architecture and all that. And WebAssembly also provides you the security sandbox and things like that. The native application doesn't have, right? So this is a quick demo that's to show you what it looks like. And let me go back to the slideshow. Okay. Oh, sorry. Okay, yeah. So we actually have done a couple of those demos. So we have a complete Redis application running inside the container. And the total size of that application is 700 kilobytes. It's less than 1 megabyte. We have a complete PostgreSQL application running inside Docker, inside, as a microservice. The entire size of that application is 800 kilobytes. It's also less than 1 megabyte, right? It's coming from the world of, say, Java, .NET, and Python. Those are pretty stunning numbers. That's also why we get engagement on Twitter, right? Because if you look at our Twitter account, it's only like 1,000 followers. But those tweets, I think they resonated with the community. So then, how it works? What did we do? To make it work, what are the standards that we leverage, and what are the things that we goes beyond, right? So one of the core things that we do is that we added an extended WASI implementation called WASM Edge WASI sockets, and it's compatible with the WASI socket spec. Meaning that if you just use the WASI socket from Bytecode Alliance, it would work with WASM Edge as well. However, we added a bunch of things. The reason why we added a bunch of things are those new features that we want. So the first and the most important thing is that we need non-blocking sockets because in a single-threaded environment, like I remember when Node.js came out, we were all extremely surprised. JavaScript is a single-threaded execution environment. How could it be possible to run a server on it, right? Because the server is inherently multi-threaded, or at least multitask, right? So to have non-blocking sockets, I think it's a hard requirement for this type of application, and that allows you to do things like multiple HTTP requests and multiple database requests at the same time, and the support DNS is another one. We can't. At the socket level, you can use IP address, but if you want to put it in Docker Compose or in Kubernetes, a lot of those functions depend on resolving DNS. That's dynamically assigned by the environment. So to be able to resolve DNS at the socket level is also very important. And then support TLS, to support HTTPS, so that we can make outbound web services calls is another very important feature for us. So we added those. So I would think this is compatible with the WASI socket, but it's a superset, right? So and then we have to go do modify Tokio and MIO and things like that to add WASM Edge socket as a compiling target, right? Which is it's tedious for us at this moment because this is not standard. So it's hard to to convince people to add this as part of their release build yet. So we have to maintain a separate fork at this moment. But but because of those, most of those works are done for our customers who, for WASM Edge users, second state customers who actually wants to use those features. So we were able to afford to maintain forks at the moment. But we are very interested in getting them standardized in the future so that those features can be part of the standard WebAssembly spec, right? So so there's yeah. Well, so the work we did is not only Rust Tokyo-based clients can work, JavaScript-based Node.js also can work, because we, like everybody else, we made QuickJS running inside our runtime, and then provide a mechanism to add new runtime functions into QuickJS, right? That allows us to add all the WASI functions into QuickJS, meaning to make QuickJS has access to the file system, to the networking, and things like that. At this moment, the support from the Rust side is perhaps the best. At least on the Rust side, all those databases are supported. And as you can see, most of them are SQL databases, and Redis is a key value store. And you can see SQLX is I would say, Rust version of JDBC, right? That's to write. It's a single SQL toolkit that targets different databases. So it has pretty good coverage for I would say fairly legacy databases, the SQL databases. But the socket support allows us to go beyond those databases because database is just one use of the socket API. Once we have a fully functioning socket API, you can do a lot more. You can do HTTP servers. You can do web services clients, right? So there's a bunch of libraries and frameworks on the Rust side we have ported to use the WASM Edge WASI socket spec. So for instance, Tokyo and Mio are the low-level frameworks. And then we have Hyper, Request, and Kafka, Redis, Dapper, and things like that. And then on the JavaScript side, we have Node and Fetch API as well. And but people say, I want more. That's because there's only so much the WASM Edge community can do to port and maintain all those forks from those, from those upstream crates without standardization. So, is there another fix that allows us to get to, more data stores and more applications? And that's where, our collaboration with Dapper comes in. So Dapper is as many of you guys know, it's a sidecar service. So essentially, in the deployment, you have a Kubernetes pod, and you have microservices here, and the Dapper here, and then the database and other services behind Dapper. So the microservice communicates with Dapper through gRPC or HTTP, and so there's opportunity with socket support. There's opportunity to rewrite that SDK, right? So that's exactly what we have done. So by supporting the Dapper APIs through their by coming up with a WASI SDK, we can currently support 26 data stores, including a lot of those NoSQL and key value stores and things like that, right? So we're pretty happy with that. And because this is a hardcore WASM conference, I think we would have to acknowledge that the way that we have done things so far are not really standard. And we want to bring that into the fold of the standardization, meaning that we want to play well with the future component model when it comes out, right? So one of the things that we have done, at least at WASM Edge, is that we have re-architected our runtime so that all the host functions are available as plugins. So essentially, the core runtime can be reduced to less than 2 megabytes, and all the the networking, the TLS, the TensorFlow inference you have just seen, and all those things can be now added as plugins into the runtime itself, right? So so the idea really is that those plugins would eventually become component model compatible, right? So we also have our own component model tooling. It's called WITC. It's written in Haskell. Well, it still have some problems, but and some of the components are already working. So that's the direction that we are going. So ideally, we want to WASI itself to be a plugin because right now WASI has a special status in WASM. It's part of the official standard. So the runtimes comes with WASI. So we want that maybe in the next version also that the runtime would not even come with WASI. WASI would be a plugin. That will allow us to target, say, non-POSIX systems, which we also have users for, like in a car in a real-time system where the underlying system is not necessarily Linux, not even POSIX, not libc, and now you need file system and socket connections to them, and you can bring in a whole different set of WASI functions into the runtime. So that's something that we are really excited about. To have those alternative WASI implementations, right? Not, so I started the story with the need to do database applications and then to do, HTTP servers, and we enhanced the WASI standard, or we expanded the WASI standard to support non-blocking, sockets and, TLS and DNS and things like that. But I think we went through that journey and we reached the point. I think we can finally meet and the standardization efforts with the component model, so that we can have a so that the whole community can have a unifying story, right? So I have 4 more minutes left, and if you guys have questions, I think you can find me afterwards. I'm gonna hang around here today all day, and I'm gonna be in Barcelona tomorrow as well, so I'm available for meetings. And so I added the slides last night because the biggest thing that happened last night was OpenAI had a plugin system. If you think about plugin system, what is a plugin system? It's to upload code so that it can be executed in the OpenAI environment. Isn't that WebAssembly is ideal for? Isn't that we have all talked about all those years, the use case of WebAssembly? It's exactly that, right? That's it somewhat saddens me to see that they're using Heroku and Fly.io to do that. They're using Container and VM to do that, to host their code. So I think as a community, we should really reach out to them and tell them there's a better way to do that, right? So, that said, enabled with WASM Edge, WASI sockets, there's lots of things you can do today with WebAssembly functions that lives outside of the the OpenAI infrastructure. You can program a microservice that receives trigger events, query APIs, store the chat history in Redis or in database, like the data store, and then execute the actions suggested by OpenAI through HTTPS through another web services called outbound web services call, right? So there are actually some examples which applications that we have created in the past, not last night, because we all have the similar idea, but in the past 2 weeks or so. So we used, we have a Telegram bot that is entirely written in WASM and compiled into WASM and running on one of our servers. What it does, if you just scan that and chat with the bot, you are chatting with GPT-4, right? You can ask him any question. You can ask them, who's in charge of Mozilla when Rust and WebAssembly was invented? Just ask that question. And if you don't have Telegram, we have a GitHub issue spot where you can go to GitHub and raise an issue. You can ask a question in that issue, and then the bot will kick in and answer your questions. I asked him, what's the plot line of Anathon and Neil Stevens' novel? And I asked him, does the Southerners really live 1,000 years? And they give really, really good answers. You can, try it yourselves. So yeah, that's. I have 2 minutes left, so I guess I can take one question. That's. Yeah, please. Yeah. Oh. Back to this. Yeah.
Hi, Michael. Thanks for the talk. The links you are showing are pointing at a repository for an organization called Flows Network. What is it?
Oh, it's because we are, struggling with ways to find the best use case for serverless functions for WASM, so to speak. So we did a lot of experimentation. This is one of our, somewhere we experiment. So it's free. We love people to come and check it out and see, if you. So it's an experimentation. It's not a product yet. It's just we want to find more use cases for WASM Edge. That's what we do. Yeah. So. All right. Thank you.